This is a very quick derivation of Einstein's field equations, where our guiding principles are: 1. General covariance. Equations are valid in all coordinate systems. And our local conservation of energy and momentum here. Newtonian limit must, number 3, Newtonian limit. It must reduce to this for weak fields and slow motion. For dependence on space-time curvature, expressed via Riemann tensor and its contractions. Now curvature is encoded in Riemann tensor, given here, and its contractions give this Ricci tensor and Ricci scalar. I'm not sure how to pronounce that. Ricci, I'm not sure, but these are the simplest symmetric tensors built from second derivatives of the metric. And our ansatz, our assumption, ansatz is a German word. This, I think, it's where we assume a kind of value and try it out, sort of thing. But anyway, we look for an equation of the form here: geometry equals matter. The left-hand side is symmetric and depends on second derivatives of the metric. The right-hand side is energy and momentum tensor here. Now, our candidate geometry tensor is Ricci tensor, or mu, which is symmetric and depends on second derivatives of the metric. Now, Ricci scalar, R, is a scalar. We multiply by metric to get a rank 2 tensor, given here, and define the Einstein tensor as such. Now, the key property is this. I'm going to say divergence here, because I'm so used to saying that. Divergence of mu of our Einstein tensor equals 0. Where our field equations in general form will be given here, where kappa is the constant to be determined from the Newtonian limit. Now, determining the weak field limit, our metric near flat space-time is given simply as this, where our h mu nu is much less than 1, and as you'll see, this is our Minkowski metric, and only the 0 component survives in non-relativistic limit, so we get this. Now, we compare this with Poisson's equation here. We therefore have kappa equaling 8 pi g. Now, we include c for the unit, so kappa equals 8 pi g over c to the 4th power. Now, this gives rise to our Einstein field equations here. Now, this relates geometry on the left-hand side to matter on the right-hand side. 10 independent equations, symmetric 4x4 tensors emerge from this, and they are non-linear in g mu nu. Now, it's worth noting that we will also, for our large scale, we would also have what Einstein referred to as the cosmological constant whacked onto the end of this here for large scale, for large scale phenomenon for his equation. But that's not really relevant for our purposes, as we're dealing with orbits around bodies, planetary bodies, or maybe later on black holes or something. So what the universe is doing way over there is irrelevant. But anyway, that's the end of this lecture. Please do like and subscribe.